Hello and welcome back to Reinforced Concrete Design. In this session we will discuss deflections and how span-to-depth ratio is used in design for deflections. Deflections affect serviceability of structures and represent a serviceability limit state condition. Excessive deflections cause cracks. Cracks can accelerate corrosion as well as affect fire performance of structures, because excessive deflections can open gaps in fireproofing tops of walls. Additionally, deflection looks bad. Even small deflections can be noticed when walking over a floor. Finishes and partitions can be damaged. Here you can see some examples of consequences of excessive deflections and resulting cracks. Eurocode 2 allows for two methods for deflection control. Deflection can be controlled by applying the deemed to satisfy method based on the span-to-depth ratio. This method depends on the amount of steel reinforcement in beams or slabs, levels of stress and reinforcement, structural geometry, and the type of structural system. In certain cases, accurate estimations of deflections are required. This includes situations where the deflection limits of span divided by 250 for quasi-permanent actions or span divided by 500 for partition and/or cladding loads are not appropriate. When design requires a particularly shallow member, direct calculation of deflection may provide more economical solutions. The deflections are also calculated for early striking of formwork and for temporary loading during construction. In the past, reinforced concrete structures tended to be stiff with relatively short spans, which did not allow for the development of large deflections. The advances in the technology and practice have resulted in more flexible structures. This occurred due to several reasons, including the increase in reinforcement and concrete strength. The increase in reinforcement strength resulted in the reduction in the amount of reinforcement required for the ultimate limit state and the increase of service stresses in reinforcement. The increase in concrete strength led to the improvement in durability and the reduction of construction time. The concrete became stiffer and could develop higher service stresses. The advances in structural analysis methods allowed for greater understanding of structural behavior and the ability to analyze that behavior quickly using computers. This allowed to produce economic designs for slabs because it was established that slab thickness is typically determined by serviceability limit states. Since slabs constitute between 80 to 90% of the superstructure costs, thinner slabs lowered the construction costs. The advances in structural analysis methods also allowed to fulfill client requirements for longer spans and greater operational flexibility from their structures, which led to an increase in structural deflections. The development of deflection in structures is affected by numerous factors, which are often time-related and interdependent. This makes prediction of deflection difficult. The main factors include concrete tensile strength, creep, and elastic modulus. Other factors that affect deflection include the level of restraint of the structure considered and stiffening by adjacent structural elements, existence of secondary load paths, stiffening, magnitude, time and duration of loading, cracking and shrinkage of concrete, and ambient conditions. The effect of deflection on the shape of slabs and beams can be reduced by precambering. In this figure, you can see that precambering offsets the level from which deflection develops, and this results in a smaller deflection. Since it is difficult to calculate deflection accurately, too much precamber is often used. This has a negative effect, especially for slabs because they remain permanently cambered. To prevent this effect, precamber should not be larger than half the quasi-permanent combination deflection, but lower values are recommended. It should, however, be remembered that precambering does not reduce the deflections affecting partitions and cladding. Deflections should not adversely affect the structural function or appearance and should not damage partitions, glazing, cladding, surfaces, or finishes. Eurocodes establish deflection limits depending on the nature and function of the structure and the type of finishes, partitions, and fixings used. Additional limitations are applied on deflections to ensure the proper functioning of machinery or apparatus supported by the structure and to avoid ponding on flat roofs. According to ISO 4356, the deflection in beams, slabs, or cantilevers subjected to quasi-permanent loads should not exceed the span divided by 250. The deflection should also be assessed relatively to the supports. Precamber may be used to compensate for some or all of the deflection, but any upward deflection incorporated in the formwork should not generally exceed the span over 250. ISO 4356 limits the deflection at the construction stage of concrete beams and slabs to span over 500 for quasi-permanent loads. This limit can be amended depending on the sensitivity of adjacent parts. According to Eurocode 2, the limit state design for deformation should be based on either limiting the span-to-depth ratio or comparing a calculated deflection with a limit value. In finished structures, the material properties, environmental conditions, load history, restraints at the supports, ground conditions, and many other parameters can differ from those assumed in the design. Therefore, the actual deformations may differ from the estimated values, particularly if the values of applied moments are close to the cracking moment. It was discussed earlier that the limit state design for deflection can be based on satisfying the span-to-depth ratio limits. More rigorous checks are only necessary for members which lie outside such limits. In the method based on span-to-depth ratio limits, correction factors are applied to the limiting values for reinforced concrete beams and slabs to allow for variations in the geometry and material properties from the basic values. It is important to note that the span-to-depth ratio limits do not allow for precamber. The basic span-to-depth ratio limit is calculated using one of two formulas, 716 in Eurocode 2, depending on the reinforcement ratio of the bottom tension steel at mid-span. As you can see, the basic span-to-depth ratio limit depends on structural system, strength of concrete, and the amount of tension and compression reinforcement in the section. The basic span-to-depth ratio limit is amended using three correction factors. The formulas used for the calculation of the basic span-to-depth ratio limits assumes that steel yielding strength is 500 megapascals and that at the serviceability limit state, the tension steel develops the stress of 310 megapascals at cracked sections, at mid-span of beam or slab, or at the support of a cantilever. The first correction factor accounts for deviations from the assumed stress in the tension steel. F1 is calculated as the ratio between the assumed stress of 310 megapascals and the expected level of stress sigma s. This ratio can be substituted with the expression taking into account the variation of steel yielding strength from 500 megapascals and the amount of steel provided over the required by the ultimate limit state design. F1 should be smaller than 1.5. The second correction factor considers the effect of flanges on the basic span-to-depth ratio limit, which was derived for rectangular sections. F2 remains in the range of between 1 and 0.8, depending on the breadth of the flange. The third correction factor considers the effect of span on the basic span-to-depth ratio limit. F3 is applied to the beam and slabs, excluding flat slabs, that are longer than 7 meters in the effective span, and to the flat slabs longer than 8.5 meters in the effective span. The parameter K considers the effect of the structural system on the basic span-to-depth ratio limit. The value of this parameter is defined in table 7.4n of Eurocode 2. For example, K equals 1 for a simply supported beam or slab. In the case of a continuous beam or slab, K equals 1.3 or 1.5 depending on the location of the span considered. Table 7.4n also gives the value of the basic span-to-depth ratio limit for two characteristic values of reinforcement ratio and different structural systems. Besides using the formulas 7.16 in Eurocode 2, the basic span-to-depth ratio limit can also be found from a design chart. As you can see, the design chart includes curves plotted based on the formulas 7.16 for different concrete strengths and varying values of reinforcement ratios. Let's consider the example of a beam made from 30 megapascal concrete. A vertical line is drawn on the chart from the value of the reinforcement ratio on the obisca of the chart. A point of intersection of this line with a 30 megapascal curve is found. A horizontal line is drawn from the point of intersection. The intersection with the ordinate gives the value of the basic span-to-depth ratio limit. And that's it. We've seen how span-to-depth ratio helps us in the design for deflection. Join me next time when we move on to discussing shear design in reinforced concrete.